Okay, hello students. So in the last lecture, we have derived or we got the eigenfunctions and the energy eigenvalues of a particle in infinite potential well. Now before moving further to some other problems in quantum physics, we have to do the scattering. Now instead of the infinite potential well, I can take finite potential well. But before moving further, let me discuss here a very important concept in quantum physics which you all have done earlier in electromagnetic theory also. So let us try to see that. We would like to get more insight about the probability density which we have discussed till now. Try to get some more insight. Okay. So now, okay. So let me now start with that. Okay. We all know that Schrodinger's time dependent equation once again will take. Okay. So we are going to get more insight of the probability density what we have discussed till now, and that we call as probability current density. Okay, don't worry, slowly we'll see what is that. Now first we'll try to write whatever we already know, the Schrodinger's time dependent equation, that is I h cross del psi by del t is equal to minus h cross square upon 2m del 2 psi by del x square plus vx, and this is psi into again x and t. Okay, here also psi is a function of x and t. Now if I say that we have to check that the probability density is given by psi star psi mod psi square, and the total, and we all know that total probability of finding the particle in space is 1. So we can write psi xt mod square. We are taking again one dimension, okay, and later on we can generalize our result to 3 dimensions. So what I am claiming, I am saying here that for example at time t is equal to t naught, if this is true, minus infinity to infinity psi star xt psi xt dx is equal to 1 at time, if at time t is equal to 0, if this is true, then we have to check that at time different from t0 again this is true. Okay, that, and while checking this we'll see that we'll get a deeper insight of this probability density. Psi star x, this I should take t naught, psi xt which is different from t naught, psi xt dx is equal to 1. So if this total probability, if I represent by p, capital P, then I can write this as, this is my probability density, this I write is as rho, and total probability I write it as p. Pt is equal to integral minus infinity to infinity rho of x dx, rho of xt, sorry. Okay, this is my probability density. Rho is my probability density, the probability of finding the particle at some point x and t, and when I add everything that will give me total probability that is equal to 1. Okay, this is equal to 1, that we have to check, and already what do we know, capital P at t naught, this is equal to 1. This I am saying it's true. Okay, And now if I take the rate of change of this probability, if pt is 1, then dp by dt, this will be 0. Okay, so we have to see that whether at time t different from t naught, this is guaranteed by Schrodinger equation. That we have to check. Okay, that will give me a very nice result. Okay, what will give me? That the probability is conserved. Now in order to proceed to find this dp by dt, I need to do dp by dt is equal to integral del rho by del t. Rho is a function of x and t dx. Okay, because this is probability density, is equal to integral, and what was my rho? Here I have told you rho is psi star psi. Okay, so when I take the derivative of this, I will get del psi star by del t psi plus psi star del rho by del t. Okay, this is equal to dx. Now I have already written the Schrodinger's equation, time dependent Schrodinger's equation. Now this equation I get, I again go back, and this my Schrodinger equation I make in a box. Okay, and I name this is equation number 1. Okay, this I have defined as rho, and this I name as equation number 2. Now from equation number 1, I can get the value of del psi by del t and del psi star by del t. What is del psi by del psi star by del t? Is just the conjugate of this. So from this equation I can substitute del psi by del t, and also I can get the complex conjugate of this equation. Correct? So what do I get? Del psi by del t will be how much? Del psi by del t, here this term will be directly del square psi by del x square plus v psi. Okay, similarly I can find del psi star by del t. So what do I get? So I know that if I h cross del psi by del t, this is equal to minus h cross square by 2m minus h cross square upon 2m del 2 psi by del x square plus v psi. Okay, v is as a function of x and v psi. Okay, so this equation I got here. Okay, there is no, if psi I am writing here, there is no need of this bracket. Okay, so this is my first equation. If I take the complex conjugate of this equation, I will get I h cross del psi star by del t is equal to minus h cross square upon 2m del 2 psi star upon del x square plus v of psi star. Clear? Now what I can do, I can multiply this equation by psi star, and I can multiply this equation with psi. So what do I get? I h cross psi star del psi by del t is equal to minus h cross square upon 2m psi star del square psi by del x square plus psi star v psi. Okay, this is equation number 3, 4, 5. Multiplying equation number 3 by psi star. Similarly, I can multiply equation number 4 by psi minus I h cross psi del psi star by del t is equal to minus h cross square upon 2m psi del 2 psi star upon del t plus psi v psi star. Question number 6. Now from equation number 5 and 6, I can substitute the left hand side, both the values in this equation. Equation number 2. So what do I get? Okay. Oh, sorry. There is some. Just a sec. Okay. So now So now when I substitute the values, what do I get? I get that. So what basically we are calculating here? Del rho by del t. Okay, del rho by del t is this value. So separately I will calculate del rho by del t, and then I can substitute in equation number 2. So this is my del rho by del t. So my del rho by del t, this is equal to this will be equal to, when I substitute both the values, I will get I h cross minus I h cross upon 2m. Okay, del 2 psi star by del x square psi minus psi star del 2 psi by del x square. Okay, we can see the previous equation. Yeah. Yes. So okay, so I am just writing only del rho by del t, that is del psi star by del t psi, plus I am substituting this value and this value from equation number 5 and 6. Then what will happen? Only this term is left, psi star del 2 psi by del x square and psi del 2 psi star by del t. Psi star v psi and psi v psi star will cancel. Okay, these two are same. We can just shift psi star, no problem. So I'm left with only this. This I can write as, if I multiply n denominator by I, what do I get? I will get h cross upon 2im, okay, del 2 psi star del x square psi minus psi star del 2 psi by del x square. Now there is a very nice thing to see here, that if I'm able to show my right hand side, so basically we were aiming that dp by dt should be 0 at some later time t. Okay, and what is dp by dt? Is del rho by del t dx. Okay, this is my probability density rho, and it has come out to be this. Now if somehow I can show that this right hand side is a total derivative, then what will happen? Then when I do the integral, because basically what I have to do, my dp by dt, this is equal to integral del rho by del t dx. Clear? This is my initial equation. Fine. This I have to show that this right hand side is 0. Now if somehow this is my del rho by del t which I have calculated, if this somehow I shows as total derivative, then the integral would go on the boundaries. Okay, then it will be easy for me to show it is 0, because already we know the conditions that at the boundaries limit, when x tends to plus minus infinity, my wave function should vanish. And also I want my derivatives to be bounded, del psi by del x, okay, at plus minus infinity, limit x tends to plus minus infinity, this is bounded. In such a case, these conditions are required. Okay, at infinity my wave function should vanish. Now if I make this as total derivative, then the integral would go as boundaries plus minus infinity, and already I know that my wave function, it goes to 0 at plus minus infinity, and my derivatives are bounded. And indeed I can show this as, from here, how can I write? Del rho by del t is equal to h cross upon 2im del by del x of, I can write this as, okay, this is just, I can, there's little some less space, del psi star by del x, psi minus psi star del psi by del x. If I can write this my integral, when you open this you will get this. So we are very lucky that this can be written as total derivative. Now when this becomes total derivative and I integrate this in this equation, my main equation, yes, let me define this as a, in this equation, then what will happen? It will go on the boundaries, correct? Now let me define this as, we can take we can write this as del by del x. This is a constant I can take inside, h cross upon 2im del psi star by del x minus, sorry I missed psi star del psi by del x. Okay, this is a big bracket. This if I define as J, that is probability current density, then what do I get? Then what was my equation number? 6, 7, this is 8. Okay, so I have written equation number 7 as a total derivative of equation number 8. Now from equation 8, let us define, we will try to interpret, okay, whether I'm defining this as current probability current density, whether this is correct or not, this whether it is justified or not. Okay, let us define J of xt. In different books the different symbols they have used, but this is standard symbol, so I'm using J. Okay, Jxt as h cross upon 2im psi star del psi by del x minus psi del psi star by del x, correct? This I defined as probability current density, and then by defining this G we get del rho by del t, this is equal to minus del j by del x, correct? Because here what do I have? Del by del x, there was a minus sign, yeah, here. Okay, when I substitute I will get, and del by del x of, and this I define as del psi star by del x psi. Okay, I have taken minus sign common here, so I will get a minus here. Okay, and then del rho by del t plus del j by del x is equal to 0. And also from this equation I can see that what is my J? Psi star del psi by del x minus psi del psi star by del x. If I integrate, what will I get? J at plus infinity and j at minus infinity, correct? And because psi and psi star goes to 0 at plus minus infinity and the derivatives are also bounded, so I will get right hand side is equal to 0, which I can justify that my dp by dt is equal to 0 at later time t also. And what does this physically signify? This equation. This signifies current conservation. So we started with probability density rho, and then we are led to the current. Signifies current conservation. We started with probability density rho, and ended up current, existence of current density, probability current density J. Okay, now I have done this in one dimension. If same result I would like to write in 3 dimensions, then how do I write? Okay, this is del by del x. You all know that there is an operator del. This operator, what is this? This is del by del x I plus del by del y j plus del by del z k. So now in one dimension I got del rho by del t plus del j by del x is equal to 0. Correct? Now if I want to write this in 3 dimensions, what do I get? This is xt. Okay, this is also dependent upon xt. Del rho by del t plus del dot j. Okay, this is equal to 0. This is my equation in 3 dimensions. In 3 dimension. And now we can see that already I told that dp by dt is equal to, this is the existence of current. So dp, again going back to my original equation, already I've explained, I got minus infinity to infinity del rho by del t. Okay, in one dimensions if I want to see, what will I get? Minus del j by del x. Okay, and what is j? J already I have defined, h cross upon 2im psi star del psi by del x minus psi del psi star by del x. Okay, when I do this integral, j at x tends to infinity, psi and psi star, they will go to 0, and del psi by del, their derivatives are also bounded, so this is 0. It means that it is consistent. This is equal to 0. So it means the Schrodinger equation is consistent with the Schrodinger equation. Wow. So this is a very beautiful result. So we started with the probability density, and you all have seen the same result in electromagnetic theory. The total charge is conserved. What does it mean? Basically, this is my continuity equation. It means that the total probability in space is conserved. If locally I want to see that somewhere the probability is changing, then it cannot suddenly appear somewhere else. There has to be some connection of the change in the probability density from one place to another, and that led to the existence of the current. Same thing we saw in the electromagnetic theory, that if any volume, if any charge is bounded inside the volume and it is disappearing, then it means some current is appearing from the surface of that volume. Okay, we can see that. For example, if I take, we can check the local conservation of probability density. If I take total p t, this is equal to integral rho xt d cube x, okay, in 3 dimensions, for example, if I'm taking, then dp by dt is equal to integral, this integral is over whole space, okay, del rho by del t d cube x, and I have calculated del rho by del t in 3 dimension is minus of divergence of j, okay. And from Gauss's law we know that if there is any bounded volume, then that can be connected to the surface. The volume, it can be related to the surface, the flux coming out of the surface. So J basically has probability current density has the units of probability per unit area per time. One can check that. That would be a good exercise to see. Now from Gauss's law, this can be written as minus integral, this is over whole volume, okay, J dot dA, okay, dp by dt. dt at time t. So this clearly signifies that whenever there is a change in the probability at some place, then it led to the flow of the current. It has to be continuous. That is why we call this as continuity equation. Okay, this gives us more insight to understand what is the physical significance of the probability density, total probability. Okay, if some place it is decreasing, it has to increase somewhere else, and it is led through the current. If I know in some place I want to know the probability density, I can see the currents at the boundaries. It has to lead with the current density. Okay, if the particle is moving, the probability of finding the particle at some place moving to the other place is connected with the probability current density. So J is my probability current density, okay, rho was my probability density. So there would be a nice exercise to check the units of J, okay, that will be the flux, number of particles moving per unit area, the probability current density, probability per unit area per second, probability per unit area per second time, okay, one should check this. Okay, so this was all about it. It was, again, we got a very nice result. What we have, so this, whatever we are doing is consistent, whatever the people already knew. In electromagnetic theory already it has been proved, the total charges conserved was led the Maxwell to understand the different equations. Yes, so now we will further move using this concept to further solve many problems in quantum physics. So in the next lecture we would be doing the scattering problem. Okay, there we would require to find the different coefficients, how many particles they could cross the boundary per unit area per second, which would be the probability current density, and that will again give us more insight of quantum physics. Thank you.